please. Hello, dear colleagues, ladies and gentlemen. I'm glad to meet you again in the webinar of the optimization of crop irrigation under the risk of salinization using agrohydrological tools that will be guided by Dr. Mason Rasey. And with us, Dr. Mason Rasey and as well Dr. Maria Koniuskova, that will collect all questions and will convey to the presenter for adequate answering and advice. And so for I see that people is now entering, and maybe some of our colleagues of the network were a bit disoriented because we have in Europe we have changed the clock for 1 hour to adjust to what we call winter time, and that makes a delay of 1 hour. So if this happened, I'm sorry for the inconvenience. And so for those that you did not attend the first part of this webinar workshop, you can find the record of the first session that develops the basics of the modeling and about the model in particular that will be used, the Hydrus one dimension. And today it is a practical application and data sharing, and it's a session of hands-on. And for that, Dr. Mason Rasey has prepared a data set that can be shared with you through a link that Dr. Maria Koniuskova will share in the Google Disk. So again, thank you all. I hope that this will help you for improving your capacities and to be ready to make a modeling of the salinity management in salt-affected soils. And I have nothing more to add. The floor is yours, Dr. Mason Rasey.
Yes, thank you so much, Professor Batalos Salas, and I would like to welcome to all the participants and thank to you and also Dr. Koniuskova for preparing this webinar. As you remember, in last session, we talked about the modeling, the approach that we try to find out the solution. And later on, we had a step-by-step putting data into the model and explaining the model itself. So if you lost the session today, we want to put the data in the model itself step by step. And I would like to share the data set with you. And I hope you actually install the software on your PC and follow me to see what's happening and trying to put the data. We have two examples, actually one example and two scenarios to see if we change the irrigation management, what would happen to soil salinity and sodicity. So did you install the software on your PC? If yes, please put number 1 in the chat. Yeah. Cool. I see some of you are already installed the software, and then probably most of you know about the modeling and know about the Hydrus, and maybe it's repetition of the talk and then the approach. But anyhow, we are together try to solve one problem for the moment as an example. Okay, Maria, could you please send the link of the data so the participant can use the sheet file, the data from the Excel file. So, okay, thank you. Yeah, and also put please the link of the PC Progress website to download the software, the tool. Okay, I will go to the model. And if you open the, just a moment, I will share the, can you see the screen, the Excel sheet?
Oh, fine. Yes. Can you please zoom out?
Yes,
Zoom in.
of course, of course.
Yeah, good.
Okay. Dr. Kanyushkova shared the link in Google Drive to download this file. And actually in this file, in upper boundary condition, the data is provided based on the somehow measured data from for ETO, and leaf area index is estimated from as in the optimum condition. The exercise is we have a profile, we have a saline profile, and we have yeah, it is dedicated to 8,500 square cubic meter of water for leaching and irrigation. Requirement of the, for example, wheat. And normally people use 20 centimeter as a pre-irrigation, which is happening in area of Pakistan, in Balochistan of Iran, and some other part in the region, and also over the world. And after that, like 10 days to 2 weeks, they try to plant. And when the crop start to emergence, they try to give some water as a irrigation, supplied water. And normally they give 5 times or 5 events as a irrigation, and each like 13 centimeter. And here is the data of the as an example for irrigation, like day 96 from the beginning of simulation, let's say, and 160. 136, 156, and 190. So the question is, if we use this amount of water for irrigation and leaching, how we can evaluate the electrical conductivity and sodium adsorption ratio as a indicator of sodicity for 1 year in the field. And in the second part, we will go for the triggered irrigation to optimize the irrigation scheduling using hydros. Today, we don't go to optimization procedure of the model because it takes too much time, and we need face-to-face contact to, or maybe as a workshop to explain how we can tackle with the in the calibration process.
Sorry, Mason, to interrupt you. There is a question: which crop we will test?
Wheat.
Wheat. Okay.
Wheat. Yeah.
Thank
Sorry, I forgot to put the name of the crop. So this is the situation that we explain as an example. And here we have 2 tables. I will zoom out a little bit to see we have the a profile with 4 layers with EC of saturated paste EC of each layer, pH, the texture, SOR, and hydraulic conductivity of Van Genokten parameter like saturated hydraulic conductivity, residual water content, saturated water content, alpha, and N. This is given, or you actually, if you go to the field, collect some disturbed and undisturbed sample in the laboratory, we can determine the composition of the soil and also the water retention curve. And based on the data, we can use like Red Sea software, RETC, use the water retention curve data and estimate the Van Genokten parameter or hydraulic parameter. So in the second table, we have the composition of layers 1, 2, 3, 4 in the cation and ion, and also the composition of irrigation water and the rainfall. That is in our hand, as well as in the column B is the rainfall, which is derived from the meteorological station nearby of the field, and also the ET0. Actually, if you don't have the ET0 and you have also the data of meteorological or the meteorological data, you can use those data into the model, and the model itself calculate the ET0 for you. So this is all the data set that we have. I would like to go to the model. Let me share the model. Yes.
Mason, sorry to
Yes,
interrupt
yes.
you again. So I suppose that as soon as we are in the practical mode, I will raise the questions once they appear in the chat box, in the Q&A. So the question is it possible to measure the hydraulic conductivity properties by repacking soil? I don't know what it means.
By
to
what?
achieve, I don't know what it means, to achieve the same bulk density as was in the field. I don't know what it means here.
Actually, I didn't understand the procedure that they want to do. The double
Okay.
ring, double ring, or
We will ask Kennedy to reformulate his question. Please reformulate.
yeah,
Then another question is precipitation and ET0 are in
yes.
centimeters or in which
Yes, the unit
units?
is in centimeter. Yes,
Okay,
yes,
thank you.
yes. Let's go to the model, and then I will explain you the units and other things into the model itself. So can you see the screen of Hydrus?
Yes.
Yes?
Yes, yes.
Okay. So when you open the model, you can see this window. Going to the file, say, okay, new, name it. Do you see it? Do you see the small window in the middle?
Yes, all fine.
Okay. We can say, okay, let's say, name it test. Or everything that you want. Just put the name and describe it, like testing water,
Mason, I'm
water management.
sorry again to interrupt you. But as soon as the question is about the previous steps, I think that we can address. The question is, could you show very quickly how you downloaded the model from the links that you sent?
Yes.
So that people can follow you from the very start.
Okay, okay. Then I will open the PC progress. Just a moment. Then I'll share with you here PC progress. PC progress.com English. Do you see it?
Sorry, Mason, we can see Hydros.
You can see it
Yes,
now.
now we can see. Right.
Okay.
Now we can see the link.
Okay. You open this website, and if you already registered, you can log in. Otherwise, you have to register, giving your name and the password. Okay? Now I logged in with my name, my ID, user and password. I will go to, for example, to software, Hydros applications. You can see all of the informations here, like irrigation, like applications. So you can go to the download in the middle of the window. Can you see?
Downloads.
Download, yes.
Yes.
Here.
Yes.
And you can see different version of the model.
Yes.
You see, we have Hydros here, the new version, which is, this Hydros is a mix of 1D, 2D, and 3D together. Hydros 1D 4.17, version 4.17, which released in 2019. And you can click on the link under a download column, the version like 4.17. 4.17 here, the second row. You can see Hydros 1D, and just download it and install on your PC. Okay?
Yes.
Okay, we should wait a little bit for the people who download and install it on the PC. So maybe in 1-2 minutes.
Yes, let's give one.
Or I would continue, huh? Do you agree with me to continue? Maybe some people try to follow us or not.
As far as I understand, quite many people have already downloaded who put one in the chat.
Yes.
Right. So I think that we can continue.
Okay. So again, I will go to the model. Wait. So again, from the beginning, when you open the model under the file, just click on the file, say new one, and name it. Name it just test. And for the description is irrigation. Irrigation like saline soil. And say, and yeah, push the button OK. Now you have this window, which have in the left side pre-processing, and the right side post-processing. Okay, so on the main process, just click on it, double click, and select what do you want to like simulate or evaluate. Here we want to simulate water flow, solute transport, and root water uptake. Please follow me. Simulate water flow, just tick the box. And solute transport, we would go for major ion chemistry because we have the composition of each layer. So we would go for INSAS module on the model. And for the we can also select root water uptake, because we want to evaluate if we have the plant, what will happen in the for the plant as well, because we can evaluate the water stress and solute stress on the on crop in the model. So this is for the first window. We push next. On the next bottom, here we have the geometry information, which we have to define the units of length. Here we would put centimeter. If we use millimeter, then all the information, all the data set should convert it to millimeter. If we use meter, also we have to convert to using the conversion coefficient to convert to meter. So our length unit is centimeter, and the material, which means the soil layers, we put 4, and our profile depth is 100 centimeter, 1 meter. For mass balance, we would use 1, considering a whole profile as a experiment. So we push next. Here we have the time information. In the time information, we would use like days based on the data set that we have. If we have like hours, we can use it, or even if we don't have it, we can convert it to the hours or years or seconds. Now our data set is in day, and once we want to run the model for a season, growing season, or even in 1 year, daily interval is enough. So we check daily as a days. For time discretization, initial time is the 0, beginning of the simulation. Final time is like 366, the duration of a year, let's say. And initial time is said normally it's suggested or recommended to use these values, and if you have more experience, you can change it. The initial time step and minimum time step, and it is the model started from the intervals, these intervals, to start to calculate the water flow using the Richards equation. So for the boundary conditions, which mean we have evapotranspiration, irrigation amount, and ETO, and also leaf area index of the crop. Here we would use time variable boundary conditions. And for the number, since we have the daily data set, we would use like 366 based on the data that I showed in the Excel file. If you have less, so you can specify here based on the number of data that you have. So this is this value is correspond to the 1 year data set that we have. Yeah, we can check repeat the same boundary condition n times. For example, 10 years. Just clicking it on it and put it 10 years. But we don't go for this for the moment. We want to simulate only for 1 year. So we would go to the next window by selecting next. Here the print options, which means the model asks you how many times you want to print, or number of print times based on the simulation. And if you use it, the model provides some data set based on the interval that you specify here. And here I would say, okay, I want to have like 12 as each month. And select print times, and put default, okay. which means every month it generates some extra data set to check the simulations. Of course, it's simulated in daily interval and provides you in daily interval. So we push next. And here also it's recommended to don't change these values here. Of course, in the calibration processes, yeah, we can change it based on the uncertainty of the input data and also the error that we have. And so we don't go too much, or I don't want to explain too much about it because the time is limited. So the iteration criteria is fixed as it is recommended. Again, we push next. Here, the hydraulic model we want to select. Actually, if you check different or select different models, you will have somehow different results. And you have to evaluate which model is suitable in your case. Normally, we can start from Wangenhochten and Muallim model. And if sometimes you run the model and you can see that it is not suitable, or you will have some like ill-posed simulations or unlogic data or result, then you will change the hydraulic model. So we don't want to go to hysteresis. We don't want to have a dual porosity. We have a normal soil profile. So from this window, we push next. And here we have the materials 1, 2, 3, 4, or soil layers. And there are the Wangenhochten parameters. Actually, we can use the data set from the data that I shared with you. So just go into the sheet file, to the to the Excel file, and just select the data, copy on the window. I copy here and also the KSAT. Okay, do you follow me? So here we put the information regards to the soil hydraulic parameters. If you don't have it, you can, or you don't have enough data set to generate the hydraulic parameters here, as we put here, you can use the Rosetta program, which is implemented already in the model, by selecting or putting the models, like just using the textural classes, or even having the sand, silt, and clay amounts, or having bug density, or water retention, somehow field capacity or wilting point. You can use these values, put the value, the data set that you have, and push the predict. Once you predict and accept, the data will already put into the table. Just try it, just test it. It doesn't matter what is happening. It is just test, and try to play or run the model like hundreds of times to see what is happening and learn a little bit more about the model. So push the next one.
Sorry,
and here
Nathan,
yes.
Nathan. And the question, where did you take the data? How you made this copy? You copy pasted from where?
In the table 1 of the Excel file.
We cannot see your Excel.
Yeah, just a moment. I have to again share the Excel file. Here, screen, yes. Can you see now? You see?
Yes.
This is theta R, theta S, alpha, and N. Just copy or Control C, copy and paste in the window of heights. Okay? Follow me? So again, I will go to the model. So just put all the data in Q, theta R, theta S, alpha, N, and KSAT here in the rows and columns of the model.
Mason,
So,
and I value is always 0.5.
what?
I value.
Yes, yes. For I, normally in dry land, we use it 0.05. And sometimes we can change it based on the experience or, and sometimes we can optimize it based on the water retention data set. In Redshift file, we can optimize it based on the data that we provide into them. So
maybe
that's
you
it.
can give some reference or how can it be chosen for
actually,
other regions?
As I remember, Van Genochten in 1989 had a publication on that. And maybe later on, because I don't have now, but later on I will share the document with you and you can send to the participants. Okay? Yeah,
okay.
They try to evaluate this parameter. So we go the next step, the boundary conditions. Actually, we have boundary condition with surface layer because we have like 20 centimeter of water on the topsoil as a pre-irrigation. It's too much, 20 centimeter. And you can evaluate even the boundary conditions. Here it's a conceptual of the model to see which one is the most suitable for in your case with your situation, with the field situation. And normally we can evaluate the runoff with atmospheric boundary condition with surface runoff or variable pressure head, for, as example, like drip irrigation or variable pressure head and triggered irrigation. Today we will evaluate this one as well. And as a lower boundary condition, we have different kind of situation like free drainage, like seepage, and based on or fluctuation of groundwater or variable pressure head, let's say. So based on the data set, based on the observation, we could select the lower boundary condition as well. So in our case, because we don't have a groundwater level, so we have the free drainage condition.
Sorry, Mason.
Yes.
The values of residual water content, how did you calculate or determine?
The residual, so I have to go to the previous session here. Normally for residual water content, they put in the log, or they say, okay, if it would be air dried, and if we put the soil, air dry soil in the oven, the amount of water content would be the residual water content. This is the ID. And somehow, sometimes based on the data set, the water retention, which means from the saturation to wilting point, when we put the data into like Red Sea, it gives us somehow some results as a residual water content, which means a little bit more than the air dried water. And if you have some question, you have to have some more literature on it and more experimental to see what is the difference between the let's say air dried water content, which we can assume as a residual water content, or the measured one in the laboratory. So in the in the boundary conditions, so we select the atmospheric boundary condition with surface layer, and for the maximum head, because we assume that as a pre-irrigation we have like 20 centimeters, so the head would be like 20 centimeters. Here we put 20 centimeters. Since we have the potential evapotranspiration, or ET0, and also leaf area index, here we check this box. The extension coefficient for the width or grass would be like 0.39. In the calibration process, we can play with this, and normally it would be like 40 or 40% or 41, 0.4 or 0.41. And as an initial water content, we can put as a initial water content as a pressure head or in water content, based on the observation that we have. In our case, I would use water content.
Mason, if you have subsurface irrigation, what is the boundary condition?
For what?
Subsurface irrigation.
For subsurface irrigation, you mean the drip irrigation? We can't actually simulate with Hydrus 1D. Because we can't specify the boundary condition in the middle of the profile. But with 2D and 3D, we can do so. So we push put the next icon, and we can go to the next window. Here we have the solute transport information. For time weighting schemes, we would use, or normally we can use Grand-Nicholson schemes. And for space weighting, Galerkin finite element. For mass unit, we would say like milligram.
Sorry, again, the water table levels, do you add it? Where do you add?
Just a moment. I will go to the previous one. Water table here. In our case, we don't have water table.
And if you have,
we put use variable pressure head.
Okay.
With the variable pressure based on the reference at the soil surface, we can use the fluctuation of water. Or if we using the diver sensor, we push in the borehole in the field, we have like a fluctuation of groundwater level. We have the data set. It would be like the value would be minus. They are not positive. So we can put into the mode. Okay. Any question?
Thank you. No more.
So in the next window, we don't change the it's based on the experience. You can change these schemes, but for the moment we don't change. For the mass unit, we would use like milligram. It's up to you based on the observation. You can use the mass unit. The stability criterion use the tertiarity factor. Okay, just use as a recommended one by the model. But for the composition here, we have like 6 composition of solutions. Do you remember? In the table 2 of the Excel file, we have 4 layers with 2 composition of irrigation water and rainfall. So, which means we have 6 composition of solution in our system. So we can put 6. If we have the adsorption concentration, the CEC or cation exchange capacity of the soil layers, you can use it. Otherwise, just put 0. Now I put 1 to see what is happening in the next window. Doesn't matter and doesn't affect the result of the model, because in the next window we put the value 0. So you see, I will go to the previous one. Here, this is the window. We put 6 as a solution concentration combinations, and push next one. Here we have to put the data set for the solution composition. I would suggest, and the model itself know already that it started from the layers, soil layers, and also the water, applied water or precipitation. They are the coding that the model understand. So for the first one, the composition of first layer, the second one, again, the second layer till fourth. And for number 5 and number 6, we would put the composition of irrigation water. The number 6 would be composition of rainfall. Just copy and paste the data set from the Excel file. I will go to the Excel file. Here, you can see, just copy and paste this data. There are actually the measured one. Just copy and can you see the model, Maria?
Yes.
Okay.
No, not the model, the table of solid composition.
Oh no, you can see now the Excel file.
No, Excel file, and above there is the windows of Hydros.
Okay, good. So here I will just paste them. But be careful that the data would be like, should be in the corresponding name. Like the first column is calcium, the second one magnesium, the third one sodium, and Cl. You can see the Cl is the fourth one, but in the window of Hydros is like in the 7th. Yeah, 1, 2, 3, 4, 5. Yes. And we have to change the values, the column of corresponding each ion. Okay? Do you get my mean?
Yeah. Yes, there are 2 questions. Why didn't you use 4 adsorption concentrations, considering that you have 4 materials?
Actually, I don't have the data set regarding to cation exchange capacity and GAPON, I mean the data. Based on the data, I can select, I can choose like 4, 1, 2. Okay. Once I don't have the data, so I would say, okay, 0, because I don't have the data.
And these are available concentrations of cations and soil layers.
What?
The available concentrations of cations.
Yeah, actually
what
the
are the
composition.
Concentrations?
Yes, the composition is based on the soil. There's a saturated paste solution.
Saturated bed extract.
Yes, and for the adsorption, you have to measure the cation exchange capacity, and during the procedure you can you can measure the exchangeable calcium, exchangeable magnesium, and exchangeable potassium and sodium. Okay, once I don't have the exchangeable data, so I put push 0. And however, we consider for the solute transport as an passive. not really active. So it gives you some idea how it's distributed within the profile. It's based on your data, of course. If you have more data, you will have more robust results and output. So here, I just put the values of solute composition based on the given data. Okay? I will go to the next. So again, since I don't have the kinetic data of precipitation and dissolution, silica solution, so I leave this window as it is, like 0, maximum number of iteration 1. Go to the next. So in the next one, we have again the materials, and in this first column is the bulk density of the material. I would say like 1.5 for the moment is okay for the layers. And this is the diffusion of solutes in free water, and I would use like 2. And it's depend on the experiments and experience, you can change it. And for the dispersion coefficient, normally in the literature, you can find out that 1/10 of soil profile would be the good or initial estimate for dispersion. And once you want to calibrate your model, you can also calibrate these values, the dispersion coefficient of solutes here. Since we don't have a CEC or cation exchange capacity, calcium, and other things, we would use like 0. Push up, select or check all the data. This is the Gapon coefficient here for calcium ratio, calcium magnesium ratio, calcium sodium ratio. And once we don't have it, we put 0. And the model simply simulate the salt movement and flow throughout the profile, and it is not too much different with the somehow with the high saline or sodic condition. So here we push next.
One question.
Yes.
Is the column in the solution composition and in the model, so and the Excel file are not the same
here?
So you know, the titles of the columns are different in the Excel table and in the model.
Yes, I told
but
you.
It's the same. But it's the same, right? So you can rename, and that would be fun.
Actually, you should check the data. Let me, because I didn't check the data of that, immediately go to the hydros. You can copy and then column by column. For example, for chloride, just copy the column of chloride, put it here. For sulfate as well, for alkalinity as well, column by column. Okay?
Okay.
They should be correspond to the values which is provided in the table. Any question? You see here the chloride is like 150, and in the table also it's 150. You see? Can you see the Excel file?
Yes.
Okay. So here we have this one. Where we talked about
I don't know if so the concentration of potassium K plus in 6th row. In which row?
The potassium.
There is no potassium.
Actually, we didn't measure it, and I didn't put it here. I think just put like 0.1 or 0.2. Doesn't matter too much.
So you put the minimum values.
Yeah, the minimum value,
manually.
because I remember we didn't measure that one, and we, based on the experience, and I asked the specialist, and they said, okay, like these values would be enough, because others like ion cation is too much, so we don't have enough too much potassium here. Just that's just an example, you know.
Okay,
we need the real, yeah.
You can move on.
Okay. So here we put the solute transport and reaction parameter, because we want to evaluate the passive flow. So for the solute transport boundary conditions, because we have the concentration, because we have like a different composition of water and rainfall, we put like different flux, different concentration flux, based on the value, the amount of water which comes, which means we have different flux of concentration. For lower boundary condition, we would say like zero concentration gradient, which means that in the equilibrium with the deeper part of the profile. And as an initial condition, we would say like in liquid phase, because we measured in saturated paste solution, so we would use like liquid phase. If we have the total value, then we would use like total, but we use the liquid phase concentration. Okay, we will go to the next window. Here we have to select the water uptake model, root water uptake, based on the FRIDIS or S shape. And here I would like to use like FRIDIS model, based on your experience and also the situation. You can use like S shape. And solute stress model, you can say, okay, no solute stress, or additive model, or multi-active model. You can find somehow some results, some information from the literature to put in into the model. But here I don't want to go to the solute stress for the moment and put 0. And for the critical stress index, I would say like 100%. If we have like any stress as a like solute, then the crop will experience somehow the stress based on the solutes. So for the passive root water uptake, I would say if the like electrical conductivity like 6, the crop can collect some uptake some ion and cation from the soil, and this amount could be like logic for wheat. And you can also find out based on the crop from the literature, which would be the number that's suitable for C root, which means the passive root solute uptake. So we will shift from this window, go to the parameter of root water uptake, and we can specify this value for FAO-GSP parameter based on the data that we have, or based on the data set that already implemented into the model. Here we can by pushing this bottom on the down of the bottom of the window, we can select the crop that we are trying to simulate, or we have in our field, like grass, like lettuce, tobacco, and sugarcane. But in our case, like potato, in our case we have wheat, and we select that one. And just a moment, I should. Yes, you can see this is. And what this value says us, it says, for example, P2H means if the like pressure head or metric potential in the soil reach to the -500, the plants try to give some more energy, or spend more energy to collect some water and also nutrient from the soil. So if it's reached to like minus 900, it means it experiences like a stress. And P3 is like wilting point, the metric head of wilting point, which means the crop will die. So the optimum value is somehow between like minus 500 and minus 1, which means saturated or near saturated condition, and somehow like field capacity, minus 500, let's say. Okay, just select as the data set of the model, push next. And now here we have to put input the time variable boundary conditions. As a time in day in the first column, precipitation, potential evapotranspiration ETO, leaf area index, C-top, and C-bottom. C-top means concentration at top of the soil. C-bottom is the concentration, if is any, coming from this bottom of the soil, you can put here. So we will go again to the shape file. Can you see it, Maria?
Not shape file, Excel table.
Excel file, yes, Excel file.
Yes.
Do you see it on the screen?
Yes.
Okay. Here we have the time, which means start from 1 to goes to like 366 or 65. This is our data set that we have, okay, for 1 year. And for the precipitation, we got some data from the like meteorological stations, and also based on the definition or the like as an irrigation, we have 5 events of irrigation and 1 time for pre-irrigation, which means here 20 centimeter as a pre-irrigation at 30 day of year. I put it here in red, added to the value of precipitation. You can see here.
Yes.
At time 30.
Yes.
And we have like on 96th day, we have like the irrigation. Again, I add this amount, like 13 centimeter to the precipitation here. 96. You can see? Can you see?
Yes.
Okay. Also, I followed the procedure and I add for the different event, like here, 36 and 156 day. I added the 13 centimeter of applied water, and also 196. So this is the precipitation. And the reference evapotranspiration, which is comes from the meteorological station. However, we can calculate by using the Allen equation or FAO-56 publication, or getting the data from the meteorological, just put on the model. This is the fourth column is the surface potential, which means the maximum head of the at the demand of the atmosphere to collect some water from the soil. We put like 100,000. Okay, for the leaf area index, if we have some data, or if we measure leaf area index by image processing, by like different devices in the field, in some like in weekly interval or daily interval, we can interpolate it in daily as it is now, and yeah, put in the corresponding day. Like it's started, or emergence is started from 57, the day of 57, and goes to like 2-4, the maximum, and again becoming low at the end of the season because it's already harvested, let's say. So this is the data set that measured in the field, and with some data for as an irrigation. Here in the C-top, let's go to the model. You see C-top. Can you see it?
Yes.
Okay. In the model we have C-top, and here in Excel file we have C-top. Here we have to define the code of composition. If we are as a precipitation, if we have rainfall, we would put like 6 because it's correspond to the composition of rainfall, which we already put into the previous window as a composition solution. Do you remember that? The number 6 is rainfall, and number 5 is the irrigation composition, the water of irrigation composition.
Sorry,
Here
Mason, there are several questions.
Yes, yes.
LAI should be less than 1, isn't it?
Leaf area index?
See.
No, leaf area index started from like near to 0 at the emergence.
Yes.
And it goes like to 4, 1, 2, 3, 4.
So it can be
become
more. It can be
less.
more than 1.
Yeah, more than 1. Yes, yes. For example, for maize would be like 8, as I remember.
Another question is that if your time column, is it a Julian calendar or another calendar? Maybe the days are not concordant.
You have to convert it based on the simulation that you have. If you start from the beginning of a year, you have to define the DOY of your measured data, which should correspond to the day that you measured in the field and you put into the model. You know, it's based on the situation that you have and your selection. Here I started from like as you see.
But you put 366, but the typical year is 365.
Oh, you can use it 300.
Okay.
Or even you can use it the growing season, like 240 days. Or 200, let's say for wheat, like 200, 210 would be enough. But here in this example, we want to evaluate because during the autumn and winter we cultivate wheat. In spring we harvest the wheat, and during the summer we don't cultivate anything because the weather doesn't allow us to cultivate anything in the region.
Okay. Then another question is, if the rainfall, what if the rainfall occurred at the same time as irrigation for some reason, unforeseen? And should you recalculate the funnel concentration of the
yes, the model itself try to calculate everything, you know, based on the composition that we put into the model.
Then so they propose to put a new C-top, for example, 5.5.
No, it's impossible to put 1.5. As a C-top,
5.5, sorry.
As a C-top, we have like 1, 2, 3, 4, 5, and 6 in our case. If you have more layers, you will have the different or less layers. You would change this code. This code 6 and 5 in this example correspond to the composition of input water as a precipitation or as a irrigation. Okay?
Okay, thank you.
Okay, cool. So we would put all this information into the model. As a CBOT, we would put 0 because we don't have any concentration from or measurement from the bottom of the profile. So I copied all the data and put it here. Just paste it. You can see I put all the, copied all the data and put it here. Because in some years are like 365 and some year are like 66. I use here 66 as a number of day. And yeah, I just use these values as a that's repeating of the 365. Just check it. And this is the time variable boundary condition data set that we already put into the or enter into the model. So we go to the next. Here we get a message from the model that do you want to run the profile application? We say next. And so far we didn't specify any observation point in the model and also the root distribution. Okay. And also the initial, the value of initial condition like water content or water potential. So in this window, when you say next, it gives you some data, but we leave it for the moment. We close it. And you can see here in the left side, soil profile graphical editor. Can you see it? I am trying to move the mouse locator here. You can see soil profile. The second one from the bottom.
Yes.
Soil profile graphical editor.
Yes.
Can you see it, Maria?
Yes, we can see.
Okay. I just click on it. It gives you, do you want to save the data? I would say yes. And here, the new window is opening. Can you see it?
Yes.
Yes?
Yes, yes, we can see.
Okay. In this window, we have to specify the discretization of the profile, which means the model try to run the step by step based on the layering of the log, or let's say discretization, discretizing of the soil profile. Okay. And here we have to go to conditions. In the next option is discretization. Here we can modify the discretization. We can say, okay, at top of the soil, we have more process, and I would like to focus on the topsoil. Or even I would say, okay, leave it at it is as a standard one. And later on, if you want to calibrate your model, you can do the discretizations. There are a lot of literature on it, and you can find out more. So I would say, okay, we have like 101 nodes as a discretization. It's already implemented and is a default into the model. By edit the nodes, you can put the number, density, and using the default values, default discretization number here. So I don't want to change this discretization for material. Okay, we are going to the condition again, put the material distribution. However, there are several icons here. There are also the information that is in the menu bar. if you go like here, you can see in the discretization here, the icon is the material distribution, or in the condition, we can select the material distribution. Here, we have to define the depth of the material that we have. If you go to the Excel file, you can see the depth of the each layer. You see 0 to 13, 13 to 28, 28 to 64, and 64 to 90 or 100. Let's say from the 64, we could say, okay, this is goes to the 100. So here, it's already one materials. I put edit condition in left side. Just go to at the bottom of the window, you can see Z equal to -10. Can you see it? Here.
Yes. Minus
now
100.
it's now is -100, which
Yes.
means bottom of the profile.
Yes.
And here is 0 is top of the profile. And from 13 to 28, just go to 28, just select it. The material index would be 2. And I say, okay, 2, say, okay. The red one is material 1 or layer 1. The blue one is material 2. Again, for the third layer, I again push the edit condition in left side of the window, go to the -228, click on the discretization layer, and then go to 64. Can you see? And here, the index would be 3, the layer 3. So the green one is layer 3. And from 64 to the end of the profile would be layer 4. Now we have 4 layers, which means now we defined already the layers, the depth of each layers here. And here we gave some codes, 1, 2, 3, 4, which correspond to the composition that we already put as a solution composition. This is for material distribution. We will go for root distribution. Based on the observation in the field, you can see that the root distribution is somehow different. It's started from 0 at the top. It gradually increase till like 15 centimeter or 12 centimeter, and from 12 centimeter to like 30 centimeter reducing. So
sorry, Mason, where
yes,
can
yes.
we see it? We can see the green line. Oh, to the left.
Here on the left.
Ah, okay. We can see.
Yeah,
okay.
I will go to the, for example, to the condition here. Just select the third one, root distribution. Or here, the icon, you can see the crop with the root. Just click on it. And you can define the distribution of root. I would use like from top to like 12. Start from 0 to 100%. Concentrated, the root is concentrated like in 12 centimeter with 100%. So from 12 to like 20, 25, it started from like 100% at the top value to 0. You can see it shows us, this window, it shows us the root, the density is increased from topsoil to 12 centimeter and increased from 12 centimeter, decreased from 12 centimeter to 25. You can use even the uniform. They say, okay, from top to 20 centimeter, it would be like 100%, just it. But now I would use these values. And now we go for observation points. Sometimes if we go to the field or we want to evaluate based on the depth of the soil profile, if even we don't have any observation or even any sensor in the field, or maybe we go to the field in weekly, collect some data, some soil from different layers and measure electrical conductivity or solution composition. So, which means during the growing season, we have several data sets. And we have to specify which depth we collect. So here we can say, okay, by inserting in the left side, put just click, left click, and put in the discretization like at the top one, and like just insert like 12 here in our case, and 15, or at the bottom of the soil, just it. You can add more based on your observation, or even if you want to evaluate the different layers or different depths, the composition of solutes, you can push insert some observation point. So just once you do so, go to the condition, go to select the initial condition, because we already select the water content in the menu. And here we say, okay, the initial condition is like 0.2% of volumetric water content. And you can, based on your observation, you can say, okay, it was like 10% or even more. But in our case, as an example, is like 20% as a field capacity. So once you select your input the initial condition, just save it. Push on the if you want to close it, it asks you, okay, I want to save it. Okay, we say yes, save it. Now we save the data. It is ready for running. Now we push the button with the hand. You can see 1, 2, 3, 4. The fifth icon to execute the hydrous. Let me to execute it. And I say, okay, do you want, it asks, do you want to run hydrous 1D? We would say yes. And in 1, 2, 3 minutes, we will have the results. By clicking enter, press enter. So we have some data in post-processing, which means the model simulated soil water content and solute distribution throughout the profile. In the post-processing window, we will go to observation point. And we can evaluate the pressure head by the time. And we can select in the, you can see, we can say, show us the water content by the time. And it gives us the water content. And it shows we have like 1, 2, 3, 4, 5 irrigation. And here the first one as a pre-irrigation. Once we have a pre-irrigation and irrigation, the water content in the profile increase, and it's fluctuated based on it. There are the interval between 2 irrigation events. You can see. So this is like water content, or let's say water flow into the profile. we can evaluate as well the pressure head. You can see sometimes we have like a stress into the profile. And if you want to see you can add also the the legend. Here, you see, just right click on the window, use the edit chart data or chart designer, put the legend, say visible, the top, and say apply. Okay. And you can see we have like 4 observation points. And 1 is like at the top of the soil, and 4th is at the bottom of the profile, and 2 is 12 centimeter, and 3 is like 50 centimeter. This is the observation points, and we can say now the water content at top is lower than the middle and bottom of the profile during the growing season, based on this graph. Of course, it is not uncalibrated, it's just a run, just a test of the model to see what is happening inside the model. So if you go to the in post-processing, the second option, profile information, again, it gives you some other information based on the depth and metric head. You can see at the top, we have like more demand, which means the metric head is very low. It's minus like 100,000 to 0 in the deeper part of the profile. So you can also use different kind of information like water fluxes, root water uptake. This is the root water uptake. Like it says like 0.02 centimeter in different depth. It's actually concentrated within the like 12 centimeter, and uptake more water within those depth. So we don't consider the carbon dioxide or temperature. However, if we have some data on them, we can use as an input values and then evaluate them here. So you can see different values, different options here. If you go, for example, to soil hydraulic parameters, it gives you the hydraulic parameter of the soil for different layers, like a water retention data for 4 layers, and they are so close together. And or if you go to the runtime information, here it gives you the discretization and some information regards to the model itself, how it happened, and then just collect. You don't worry about this, and just go to the mass balance. If the mass balance is very low, like here, for example, as a water balance, if we have very low values, then we say, okay, probably the model worked very well. And it's based on the printed time, it gives us the data set. As you remember, we put the print time information, we specified each month, and it gives us the each month information, the mass balance information or errors into the model. And here we can see the model run the simulation in like 7 seconds. But it because the computer is slow, it takes more time to generate the results. So this is the information and input data into the model, but we don't see the salinity or electrical conductivity and SAR.
Excuse me.
I want to explore more. Yes.
Excuse me, Mason.
Yes.
Just consider that is 5 minutes for normal ending, but maybe you can use a bit more, but consider this, please.
Okay, just some for the rest. Yes.
Yes, please go ahead. Sorry for interrupting you.
Okay. So normally when you select the data or when you want to run the model, it asks you the name and it gives the directory of the simulations. And once you run the model generates some input files and also the output files. And if we go to like the directory of the model, the directory of the project, not the model, the project that we run already. Yes, you can see here, it's a directory is C user direct test. However, I want to go to another directory to show you. Yes. Can you see the window here?
Yes.
Yes. This is the information. Can you see?
Yes.
It's a folder of the model. I run already the project of NIM29. It's the same, the data same, were the same as we use today. And if we open the information, open the files here, just delete. For example, atmosphere in. Just a moment. Can you see? If we open the atmosphere in file, you can see all the information that we input into the model, the upper boundary condition, like the time, the precipitation, the evapotranspiration, and also T-top, C-top, which is already, we put already into the model. And I want to, I forgot to say you, if you use the model, every time if you, for example, in one window, in main process, if you select a help, it gives you some hints. What are they and how you can change them, and some basic information. Every window has this option, the help option. You can push on the help and you can see the information. It is based on the user manual of the model. And in the user manual, the explanation about table 12 explain the output result of the model. So let me show you the observation node chemistry, which means it gives us the simulation of the observation node. Here we put 4 observation. If you open this notepad, you can see lots of information, lots of data, time, calcium, magnesium, sodium, potassium, alkalinity, sulfate, chlorine, tracer element, and EC and SAR of soil profile. For example, node 1, or which we inserted into the model. The second node, which is in 12 centimeter. You see, the model try to simulate the SAR, EC of soil layers, and also the ion and cation concentration. within the profile at different time. If you open this data in Excel file, you can see the and you can actually make a graphs based on if you want to, for example, make a EC or make a like calcium and magnesium concentration during the growing season. You can make a graph here in the Excel file. Let me share with you. It's actually shared already. You can see the Excel file, yes? Okay. If you go to the second sheet, FAO, which means the current situation, that the current data that we put into the model. If you import the data from the notepad, from the output of the Hydrus observation node chemistry, and you can see, let me zoom it. We have calcium, magnesium, sodium, potassium, alkalinity. The first couple of the data set is for correspond to observation node 1 with EC and SAO. And again, start calcium, magnesium for the second observation point. Or I would put in the yellow color. And yeah, we have like the third and the fourth observation point, and with different values. If we make a graph for the like SAR and EC, we can see the fluctuation here in FAO irrigation example or scenario. We can see here we have like five peaks, which means we have like irrigation amount, and after each irrigation, the EC of soil went down, and again went up. And again, we have irrigation, again, like fluctuated. And during the summer, from like after the harvesting, once we don't have any input of water, the EC values goes up based on the evapotranspiration or atmospheric demands. And we have like a little bit higher EC values at, during the summer. If we look at the SIR, the values, we can also see the fluctuation based on the irrigation, again, at the end of the growing season and during the summer, due to the evapotranspiration, the solute comes with the capillary rays, comes up at the soil surface or at topsoil, and we can see within the 0 to 5 centimeter of the soil, we have like 14 or even 16 value of SAR, which means during the growing season, we have lower value due to the irrigation and pre-leaching or pre-irrigation, and during the summer, we have the higher values. That's why the farmers try to have a pre-irrigation before cultivation to reduce the effect of salinity for the emergence of the crop. So that's it from the scenario 1, which means we had a furrow irrigation based on the definition of the problem. Okay, so we say, okay, we have this amount of water. We want to shift from furrow to like different scenario, different irrigation system like drip irrigation, or even we have like some like a strategy to have to give the field every 2-3 days water. and to reduce the salt stress and as well as the water stress. So again, we can go to the model, and in boundary conditions, if we check the tree-grade irrigation, just check it and push next. Can you see the window of the hydros? Okay. You see, again, I will explain. In under the water flow boundary condition, I just click on it. For the upper boundary condition, I use tree-grade irrigation. Okay, I check it, push next. Here we have a new window, which gives us some options to irrigate automatically. Here we can say, okay, because the root density is located on at 12 centimeter of topsoil, so we are more interested on that region, and we would say, okay, at observation node would be the good criteria or position for evaluating the water stress or solute stress. And for the pressure head, as I explained, we can use the help option here. And in the help option, it gives us some information. What are they and what we can select and what we can put. I don't want to read it, and then I close it and I explain in the window. Here, the pressure head for tree-grade irrigation. As you remember, for wheat, for example, minus 500 as a metric potential would be starting from the stress, and the minus 900 at the threshold of upper threshold of stress. So I would say like 700 would be like a good or ideal situation for water content for example, wheat. And here we put like 700, minus 700 as a metric potential in the soil, which crop is or root is experiences with some with soil. So for the tree-grade irrigation, I would say for the irrigation rate, as an example, yeah, I just say, okay, every 2 or 3 days, I want to have like 2 centimeter of water lag time, which means like every 3 days, or I would say no, every 8 days, because I don't want to, I don't have a like tape or drip irrigation. I want to again use the furrow irrigation, but optimized irrigation scheduling. So the irrigation duration would be like 4 hours per hectare, or even less for 2 centimeter or 10 centimeter. It's just an example. Just try with this. You have to find out how much water you have in your hand, what is the real situation in the field, if you have any reservoir nearby the field, and are they available, or if you have a different irrigation system. Based on all the information or all the possibility in the field, you can define as a tree-grade irrigation parameters. For the duration, I would say like 4 hours, like 0.16, like as a like 4 hours, or I would say, okay, half a day. Just it. To see, it's just an example, just a scenario. So this is, as I remember, I explained in the Excel file for the tree-grade irrigation, use these values. Then I put it here, and I say, okay, now I run the model. Just it, based on the some extra information. Oh, I remember, I forgot to say that we have to delete the amount of irrigation that we put already into the model. So we have to go, we have to go to the time variable boundary conditions and delete the amount of water that we already put for irrigation. For the 30 day, 20 would be for as a leaching. We leave it as it is. But for the other, we can go and okay, say like 96 be the first one. Yeah. You should delete or eliminate the value of irrigation that you already put into the model as a furrow irrigation. I would say, okay, 0.2, because we have also here the precipitation. And again here, put it 0.6. Just delete the numbers 13 from the precipitation column, because we already put them as a irrigation. So okay, and I say I deleted already all of the information regards to the irrigation amount. I say okay, now I run it. Execute the model and press enter to continue. And if we go to the observation point, we can see the pressure head is different from the previous scenario, and also the water content. We had like in the previous one, we had like 5 peaks, but now we don't have it. We have like a normal one during like growing season till harvesting time, like 250, and the rest is like no water entry. So that all the information or the like you can interpret it based on your knowledge. And I want to show you here what is the information about the tree-grade irrigation, to see the timing of irrigation and amount of irrigation the model generated or suggested for us. If we go to the directory again, to the directory of the model.
Mason, there is a question about the lag time.
Yes.
So isn't the lag time the amount of time hydros waits before initiating irrigation once the trigger condition has been reached, not the frequency of irrigation?
Yes, actually you can say, okay, after how many days or how many interval of time you can irrigate your field, as I understood your, the question.
Okay.
Actually, more information about the lag and other things, it's already on the help option of the window, can explain you. And if you need further information, you can literature it and ask any question to me. And then I will try to explain you actually. But for the moment, the lag is the interval of the irrigation. So if you use the tree-grade irrigation option in the directory of the project, you will have the file under name rig. If you open it, you can see, based on the data that you input, it gives you some information. regards to irrigation amounts and the time of irrigation. Beginning of the irrigation is, for example, for irrigation event 2, it says, okay, beginning of irrigation is day 7, end of the irrigation 7, each one day. I here in a different scenario I put. So but here we don't have any, we don't need any irrigation before sowing, before cultivation, or even 10 days or 2 weeks after the irrigation. But the model itself generated some data, because the criteria is the metric potential. It's not it doesn't consider the crop. You have to eliminate some suggested irrigation events from the beginning and also after the harvesting.
Dear
And do you understand it?
Yeah. Dear Maysam, excuse me for interrupting.
Yes.
Well, we are now 15 minutes over schedule. It is clear that the model is very complex, and I think that you have presented the main aspects and as well dived also in some fine adjustments. And I think that if, it could be nice if you could encourage the participants to prepare their own study cases, and then
Yes.
To be presented some of that you select, and then
Yes.
maybe there will be the right time for making these comments. And I
Of
think
course.
that along these 2 weeks, people interested will run the program and will find some questions
Of
which will
course.
be addressed to you.
Sure,
And
sure.
so if you could you please advance what will be the next session, and with that
Yes.
we finish this one.
Actually, I am finishing all of the explanation regards to the model. This is the last last minute talk. So this is from our side, from my side for the moment. And if you go to the Excel file and if you import the data of observation node of tree-grade irrigation, you can see the EC values and also the SAR values. If we compare with the furrow irrigation, we can see the EC values increasing during the growing season, which I found out the drip irrigation, or like it somehow tree-grade irrigation is not suitable for such a condition of our profile. Just for the comment, maybe you can consider next time play with the data and explain how it comes and what we can tackle, because normally in the literature we can find out that drip irrigation better than furrow irrigation, but this here it says something else. So for the next time, anybody of you have some data set from the field, even not too much data, just share with me, or if have any problem running the model, just contact me. Maybe can share the data with me, and we can select 1, 2, or 3 examples of your work, and we can go together next time in next session to solve the problem of your case. So we need some soil information and meteorological data of your case. You can contact me by email, and later on we can do the Skype or other like Zoom to find out more. And next time in 2 weeks and next weeks we have the third session, and we want to explore your problem using the model and solve somehow the problem. just contact us or send any email to me or Maria, and Maria will contact me, and then we can share, we can talk about the situation and finalize the model somehow, calibrate or uncalibrate, and run the model.
Maria, any comments or information?
So I will share with all the registered participants the links of the recordings, and also I can invite them to prepare and share some materials of their testing data or from their fields. Maybe so we can send some specifications about the data that we need, and also based on the data set that we shared.
Yeah.
So yes, and we meet in 2 weeks' time on 12th of November for the interactive session.
Okay, in 2 days, I will try to send the required information based on the Excel file that I provide.
Okay.
You can see this is the most important information that we need. Even if we don't need the soil layer compositions, okay, because maybe we can run the model in a standard mode or a standard solute transport instead of.
Yeah, so we can formulate the minimum requirements and some
Yes.
optional requirements.
Yes.
Okay.
Yes. Yes.
So,
okay.
Thank you very much, dear colleagues attending the webinar. Thank you very much to Dr. Kuniuskova and to Dr. Rasei for presenting the model and solving the questions along with the presentation. And we wait for you for the next session that will be in 2 weeks. And in the meanwhile, data and relevant information will be sent to you through email. So thank you very much and have a nice 2 weeks, next 2 weeks.
Yeah. Thank you. Thank you.
Thank you.
Bye-bye. Bye-bye.
Bye-bye. Bye-bye. Good evening.